Today we're going to compare three methods of calculating square roots. If you're new to this channel, and essentially everybody is, this channel is devoted to studying mathematics, but also taking the math theory and applying it to actual calculations. So we'll take them to a spreadsheet and figure out how to use the math to get numbers. And today we'll look at square roots. It's a classic calculation. We'll look at three different methods that are in use. All these methods have a basic common thread through them. You start with an estimate that has a certain amount of error, and you reduce that error by finding a function g of epsilon that is approximately 1 minus epsilon. And when we get into various methods, we'll talk about what that means. And we will use that to update our estimate, because when we multiply, we'll combine a 1 plus epsilon and a 1 minus epsilon, and they'll almost cancel. They'll make an epsilon prime, which is much smaller than the original epsilon. So method one, we start with this x is the square root of a with some error. We multiply each side, we rearrange so we put the epsilons in the denominator, and we divide out a few terms. Now that's not 1 minus epsilon, but we can make it that way. We can add 1 and then divide by 2, and we can make the right hand side look like 1 minus epsilon plus some other terms, some small terms. And we can call that right-hand side g of epsilon. That's our adjustment. That's what we will use to update x. And that creates an algorithm. And when we multiply out x times g of epsilon, we get this 1/2 x plus a over x. This is a classic method called the Babylonian Method. It's also known as Heron's method. Heron was famous for his triangle formula. And it's been around for thousands of years. Now we'll calculate the update for epsilon. We multiply out the right-hand side. There's some nice cancellation. And we put that epsilon squared term in the numerator. We get some more cancellation. And in the numerator, we get 1/2 epsilon squared. That's roughly the new error. And that's much better. Let's go to the spreadsheet and see how it works. Okay, let's put in some parameters. A is the number we're taking the square root of. I is the indicator. It tells us which iteration we're doing. And then for the initial guess for x, we're going to cheat, and we're going to use the exact value but round it off to 1 digit. The reason why is that we don't want to get bogged down with a side calculation, so this is just the easiest way to get a 1-digit approximation for the square root. Although we could do that in a side calculation if we had to. And then the formula is the 1/2 x plus a divided by x. That's what's going in there right now. And you can see immediately we're getting more digits. And after 3 iterations, the digits stop changing. We'll calculate the percent difference in the estimated error. Percent difference is just the difference between adjacent calculations, and that's pretty much epsilon, but of the previous step. And we will calculate the epsilon of this step, which we use to determine whether we're there, whether we should stop calculating, by using the 1/2 epsilon squared formula. We'll compare to the actual error using the last value as the exact value. And you can see that the estimated error and the actual error are very close. So so the method calculates correctly. And well, now that we have the formulas in there, we can use our formulas to find out. Okay, let's calculate the square root of 3. Let's calculate some other values. 3.05, the reason why I chose that one is because if you notice, the estimate didn't quite converge in 3 steps, need 4. Sometimes you do need more. Now, this time I'm going to choose a equal 1 and the percentage error to be exactly 10%. And the reason why is that on a percentage basis, every time your initial guess is off by 10%, the errors will go exactly in this way. Okay, for method 2, we start off the same way we did with method 1, and we square both sides, but this time we keep the epsilon terms in the numerator. When we transform the right-hand side into something that looks like 1 minus epsilon, what we do is we subtract the right-hand side from 3 and then divide by 2, and we get 1 minus epsilon minus this other little term that doesn't make much difference. And that will be our g of epsilon. So we use that to update x, and the algorithm is that x prime is equal to 3/2 x minus 1/2 of x cubed divided by a. Now at this point you might ask the question, is this any simpler than the first method? It looks like we have 2 multiplications and a division each iteration. The first method only required 1 division. How is this helpful? Actually, we wouldn't do it this way. The method requires using a kind of a trick. And the trick is we'll put the a that's now in the denominator and we'll put it in the numerator. Of course, that changes the calculation. We'll call that new calculation y. But notice what this does. Y will converge to 1 over the square root of a. And then we just multiply by a one more time, and we get the square root of a. And so what we did is we got rid of the long division, and now we use several multiplications. Sometimes that's easier. Let's update epsilon. Epsilon prime is equal to roughly minus 3/2 epsilon squared. And that will turn out to be, it's small, but it's much bigger than it was in method 1. And as you'll see, it does make a difference. It may take a little longer for it to converge. Let's go to the spreadsheet and see how it works. Okay, for method 2, we'll copy over most of the calculations from method 1 and just adjust the calculations accordingly. In this case, the starting value will be the other starting value for method 1 divided by the square root, divided by the parameter a. And then the formula here is the minus 1/2 times y times 3 minus the parameter a times y squared. And that's what's being typed in right now. And once we have that in there, we can bring it down. And this should calculate the square root, 1 over the square root of a. And if we want the square root of a, which we do, of course, we take the last value and we multiply it by a, which in this case is in cell B5. Now, one calculation that we have to change is the estimated error term. It's now minus 3/2 times epsilon squared. So we'll bring that down. And notice if you compare the calculation to the actual error, it's similar. It's very close. Now we'll compare method 1 and method 2 to see how much faster at method 1 converges compared to method 2. So we'll look at the estimated error from method 1. We'll compare it with the estimated error of method 2. We'll calculate the ratio. We'll use an if statement to make sure that we're not dividing by 0. And bring that calculation down, we'll see that this ratio gets big fast. Nearly 2,000. Let's change the value of a. It doesn't really matter. It's always the same as error ratios, roughly. Roughly 2,000 after 3 iterations. So that means an extra iteration. We'll probably have to do 4 iterations with method 2 when 3 would have worked for method 1. We can compensate by increasing the digits, but then that takes more work as well. We need a better initial guess to make this method converge as quickly as method 1. Okay, method 3 has some similarities to method 2, but this one has a complication in that it's split into 2 parts, a left column and a right column. And these 2 parallel calculations feed into it. The left creates an adjustment that's used in the right calculation. So what we're doing in the left-hand side is we start with a, and by steps we turn it into 1. On the right-hand side, we start with a, and using the same steps, but only one of those steps instead of 2, we will turn a into the square root of a. The way we do this is we start with an initial guess. r is equal to s squared times a, which is close to 1. It's 1 minus 2 epsilon. And then it is also used in the initial guess for x. X is equal to s times a. And then the adjustment is going to be 1 plus epsilon, which is 3/2 minus 1/2 r. The same adjustment is used on the left and the right, but 2 times on the left, 1 time on the right. We update the r values by using 2 adjustments, and then we update the x value by using 1 adjustment. Now let's look at the epsilon terms. We multiply the terms out, combine, and we see that epsilon prime is equal to 3/2 epsilon squared. It turns out that the errors are extremely similar to method 2, converges at the same rate. Let's go to the spreadsheet and see how to use method 3. Okay. Method 3, the calculations are a little tricky. The first step is we have to find that parameter s, which is the initial guess for 1 over the square root of a. And we'll use the exact same value that we used for the initial guess of method 2. So we just copy that over. Then we'll copy over the first 2 columns of method 2 into method 3, but we'll adjust the r column. This calculation is s times s times the parameter a, and that should be close to 1. The adjustment is always 0.5 times 3 minus r. We use the same adjustment on the left and as on the right, but we adjust twice on the left and once on the right. So to get the new value of r, we take the old value of r and we adjust it twice, multiply it by the adjustment and squared. And then we bring it down and we see it converges to 1, which is what it's supposed to. Now we'll do the calculations for the right column. The adjustment is the same, but we just use it once on the right. We start the calculation with only one value of s times a. And then we adjust x by multiplying the previous x by 1 adjustment. We bring that down, and we'll see that it does converge to the square root. Now, this next step is a bit of a trick. It's tricky. I added a column in order to make these calculations refer to the right cells, the correct cells, so I could copy it over. And then when I copied it over, I deleted that column so I don't mess up the method 2 calculation. And then I bring over the errors from method 2 and I calculate that ratio is not very interesting in this case because it's all ones. Because method 2 and method 3 use the same calculations, they end up with the same errors. They always converge at the same rate. Now we'll do some just adjusting some parameters, seeing how they how it calculates for different values. Play around with it. This is how you learn math, is put in different values, see how they what relationships show up. Thank you.